Welcome to the Picture Language Seminar. It's December 22nd here in Cambridge, Massachusetts, and a wonderful day. And I just wanted to let you know that starting January 5th, we'll resume next term. We have 3 months of talks more or less lined up. We'll announce them in a short time. Most of them are mathematical or physics, theoretical physics, but we have 2 very interesting talks at the end of February, beginning of March by experimental physicists. On February 23rd, Zhengwei Liu will talk. And on March 2nd, Misha Lukin will give an interesting talk. And today I asked Tom Spencer if he would host the seminar. So Tom, why don't you take over?
Okay, well, I'm very pleased to host this seminar, and I would first, in spite of the fact that Arthur did not want me to say anything about this, I have to wish him a happy birthday, because today is really his birthday. So happy birthday, Arthur. And now, of course, I'm very pleased to introduce Zhengwei Liu, who's really going to tell us about brainstorming in math and physics. Zhengwei is an expert in quantum information, subfactor theory, quantum Fourier analysis, and his talk today, I think, will bring many of these elements together, and I'm looking forward to it. So, Zhengwei, please start.
Thank you, Tom, and thank you, Arthur, for asking me to give a talk on this very special date. Happy birthday, Arthur.
Thank you.
Today, I will talk about some ideas appeared in mathematics and physics. And the style is informal. Think about that you are in Arthur's office, and I will give an informal lecture. And this is what we did for a long time. And this lecture has no main theme. So instead, I will talk about some examples and fresh ideas, and some potential connections between different areas. Well, although I say there's no main theme, but while preparing for a talk, I thought maybe there is a main theme. We are somehow trying to understand different concepts through pictures. And the picture will range over different parts in mathematics and physics. Well, we will see how do we try to understand concepts by pictures. The story goes back to 2015. And I went to Harvard as Arthur's postdoc. And in the first month, in August, we explained to each other what we are working on. And Arthur told me the performance and reflection positivity condition, a very important condition in quantum theory and in statistical physics. And I explained to Arthur early work on subfactors and planar algebras. And then Arthur asked me, well, whether we can combine the 2 notions. And I thought about that for one day, and then I said, yes, we can actually combine them. And then we come up with this notion called planar algebra that makes the paraforming algebra like a 2-dimensional algebra on a plane. We call it planar algebra. And in particular, we can prove this reflection positivity condition in a very geometric way using the 2D geometric concepts. So what we have is the following. If you want to prove reflection positivity for Hamiltonian and for positive inverse temperature, and then we show this condition holds if and only if the Fourier transform of minus H0 is a positive operator. And here H0 is the restriction of Hamiltonian.
Zhengwei, you're not sharing your screen, so.
Oh. Okay. Is it okay now?
Yes, we see you.
It's good.
Hello, can you see the screen?
Yes.
Okay. So what we proved is the following. Given Hamiltonian, the reflection positivity condition holds for positive inverse temperature if and only if the Fourier transform of minus H0 is a positive operator. And this H0 is the Hamiltonian, the restriction of the Hamiltonian on the reflection mirror. So actually this condition is very easy to check. So in this way, we can prove reflection positivity for a large class of Hamiltonians. And the key idea is the following. The reflection positivity condition corresponds to a horizontal reflection on the 2D plane. And the usual C-star positivity coming from Hilbert space and operators corresponding to a vertical reflection. And the Fourier transform in this planar setting is a 90-degree rotation. So that relates the two different reflections. So this Fourier transform, it may not be a apparent operation in the usual setting in parafermi algebras, but it is a very good transformation in the framework of planar algebras. So in this way, we can prove reflection positivity in this geometric way. And first of all, we prove reflection positivity for Hamiltonians on other models, like the Levy-Wen model in general. And here, we want to talk about the general situation. In this talk, I will focus on the Z2 case. That means the parafermi algebra is a CAR algebra. It's generated by Majorana fermions, Ci. So Ci square is 1, and CSCJ anti-commutes. And moreover, we have a trivial state. It takes 1 at the identity and 0 at other words. So first, we can have a pictorial representation of this CAR algebra. We write a bullet we call charge on the S string to indicate the operator Ci. And then the multiplication goes from bottom to top. So we can glue the pictures. And then we can write the Ci multiplied Cj as the 2 bullets on diagram. And when we change the order, we get a minus sign. So the anti-commutes. And Ci square is identity. That means if we have a pair of charge on the line, then they cancel each other. So what's the advantage for using planar algebras to understand this CAR algebra? We not only have those vertical lines, but also we have other lines on the plane, like the cap and the cups. And then we have additional relations, like the value of the circle is delta. Here we take delta to be square root of 2. And then that implies the following relation, the resolution of identity. So 2 vertical lines corresponding to identity. And the other 2 terms on the right corresponding to the minimal projections on the basis 0 and 1. So identity is the sum of the 2 projections. And moreover, the trace also has a diagrammatic representation. We take the element in the parafermi algebra or in the CAR algebra, and then we add those caps on the right side. And that diagrammatically defines a trace. And actually, in general, if we take arbitrary value delta, this is still well defined, but the algebra is bigger than the CAR algebra. And we can show the trace is positive if and only if delta square, this value is 2 times the Jones index. And here we take the smallest case. When delta square is 2, this bigger algebra is identical to the CAR algebra. So we can use the extra relations to study the CAR algebra. And when I present a talk in the seminar, Alex Wozniakowski, a student at Harvard, he pointed to us that those pictures might be useful for quantum information. And a baby idea is the following. If we look at the CAR algebra with 2 n generators, then it's isomorphic to the nth tensor product of 2x2 matrices. And this is the well-known Jordan-Wigner transformation. So using the CAR algebra, we can understand n-qubit transformations in a diagrammatic way. And we call this model the 2-string model because essentially we use 2 strings to represent a single qubit transformation, just a unitary in 2x2 matrices. And in addition, we can also use those planar pictures like the cap and cups to represent the concepts like qubits and measurements in quantum information. And moreover, for a single qubit case, there are 4 important cases, the poly XYZ and identity, and all of them can be represented by the pictures. And for poly Z, we have this 2 charge on a horizontal line at the same height. That means we define this using the interpolation. We need to be careful because Ci and Cj, they do not commute. So it does not make sense at the beginning if we put the 2 charges at the same level. But if we take the square root of -1 as the interpolation, then we can define it in this way. And this is actually used in the proof of reflection positivity, because we want to put a picture and its mirror image at the same height, and we need this interpolation. Well, here we can study some concepts in quantum information in a pictorial way using this planar parallel algebra. And first, we try to design protocols, in particular protocols for quantum communication in a topological way. And the idea is the following. The communication only change the physical location of information, but not the information itself. And this can be captured by topological isotopy mathematically. So in this way, we can understand communication protocols using pictures and moving the information on the plane and represents the communication. So we can design various communication protocols. And Renato Renner suggested us to study multi-parted communication when we visit him at ETH. And one question is, if we want to implement non-local gates, somehow we need the entangled states at the beginning, because the gate is non-local. Say we have 2 persons, Alice and Bob, and they have 2 different computers, maybe quantum computers, and they cannot implement a non-local gate like a C0 gate, a 2-qubit gate, directly on their own computer. They need some entanglement shared at the beginning, and that's considered as a resource. So now, if we have n body, like n parties, if they want to share n non-local gates, so how many entangled states as a resource do we need at the beginning? So first thought may be, okay, if we want n non-local gates, we may need n entangled states as a minimal requirement at the beginning. But later we realize in a pictorial way, actually 1 is enough. And this was actually quite surprising at the point, since we only need 1 entangled state for the n body. We call that the max state. And then we can implement n non-local gates, like T1 to Tn, shared by the n parties. And this is a quantum circuit, and it's designed by our pictorial language, the 2-stream model. And then we realize, okay, in this circuit, we have an entangled state at the beginning as a resource. And for the 3-qubit case, this max state has the following representation: 0, 0, 0 plus 0, 1, 1 plus 1, 0, 1 plus 1, 1, 0. So that means the sum of all the spins is 0 mod 2. We take all possibilities. And then we check the literature. We realize the usual resource state used in quantum information for multi-body system is the Greenberger, Hall, and Zeilinger state. It has this formula: 0, 0, 0 plus 1, 1, 1. And then we check the properties. Well, they're pretty similar. And then we realize, okay, if you apply the Hartmann gate, this discrete Fourier transform, on the basis, then we obtain one from the other. So that means the 2 states are actually the same, but we are reading that in 2 different bases. And then we saw, okay, in our approach, what comes in a natural way is the max state, not the GHZ state. But maybe there's a more general language. We can get both at the same time, as well as the Hartmann gate. So we want to understand all those concepts in a pictorial way. Then we need to extend the 2-stream model to a more general picture language, which we call the 4-stream model. And this was also well known as the Majorana zero modes. And I will refer to a recent survey of Sama, Friedman, and Nayak on this very beautiful model. The idea is now we represent a single qubit, not using 1 cap, but using 2 caps. And but the total gradient of the 2 caps, namely the total charge, has to be 0 mod 2. And then in this way, we can represent the single qubit case pictorially. not only for the Pauli matrices, but also for the Hartmann gate and another gate, S gate, this diagonal matrix. And in this way, we can also represent the GHC state and the max state pictorially. And here I want to clarify that even though we write identity in two different ways, one has fall through strings, and the other one has fall through strings, which has full charge. The two diagrams are not the same in the CAR algebra. They are identical when they're acting on this neutral subspace, the qubit 0 and 1. So diagrammatically, they are not really equal. So, and that actually caused problems to study those diagrammatic representations. So one notation is the following. We can define this gradient operator to capture the neutrality of the underlying Hilbert space of two caps. So we take this gradient operator to be sum of the fall through strings and the fall through string with charge. This is a projection. It maps the four-dimensional vector space, the two caps with charges, to the two-dimensional subspace with neutral charge. So we call that the gradient operator. And in this way, we can represent some multiple qubit gates. Like the C0 gate is 2 qubit gates using 8 strings from top to bottom. But we need to pair the boundaries 4 by 4 using this gradient operator. On the left side is the picture in the Fosbury model. Excuse me. On the right side is the usual tensor network notation. The trivalent vertex represents the identity tensor, so 0, 0, 0 plus 1, 1, 1. And in the middle is the Hartmann gate. And they represent the same gates, but in two different languages. On the tensor network, we use the seq string to represent a 1 qubit transformation. And here we use 4 parallel strings to represent a 1 qubit transformation. And that's why we call this a 4 string model. And since we cut it on the 4 string using this gradient operator, so we call it Majorana 0 mode. We are looking at the 0 graded parts. And in general, if we want an n-qubit gate, we need the elements in P4n, the CAR algebra with 4 n generators, and we pair the boundaries 4 by 4. And that's an n-qubit transformation. Well, at that point, we observed that there are several examples indicating that we should extend the 2D theory to 3-dimensional. For example, this 2D C0 gate has a very natural pictorial representation in the 3D space. So think about identity tensor as a letter T. We replace this thick line in tensor network by a cylinder, and the boundary of the cylinder corresponding to the 4 strings. And then we write the identity tensor as a letter T on the right with thickness. And now when we glue the two letter T together, we need to rotate the boundary by 90-degree rotation, and that's the Hartmann gate. And in this way, we get a 3D pictorial representation of the C0 gate. And there are other observations. One important one comes from chiral conformal field theory, where I studied with Feng Xu on the so-called n-interval Jones-Boltzmann subvectors. We also see this max state, but it has a quite different meaning. And eventually we come up with the 3D theory. And the reason that is the two max states with different meaning appeared in two different 2D subtheory of the 3D theory. And there is an additional symmetry in the 3D theory. In that way, we can relate the two different subtheory by a new duality. And then we get the same formula. So what's the 3D theory? That's the QL language. In the paper with Asa and Alex, we introduced this QL language as a 3-dimensional picture language for quantum information. So it's similar to the Majorana 0 mode, but the difference is we do not use the gradient operator to cut the 4th string. Instead, we put the 4th string in a cylinder, and we put the whole diagram in a surface with boundaries. And here it's a 2 qubit gates. On top, we have 2 input disks, so 2 input qubits. And at the bottom, we have 2 output disks. And on the surface, we have additional data given by braided charged strings and captured by the Ising category. And all those pictures give you a functor in the sense of topological quantum field theory. So each picture is mapped to a gate or linear transformation. But here, we require that this map, the corresponding gate, is defined projectively. So it's defined up to a face. But this is good enough for quantum theory because in quantum theory, the gates are defined projectively. And on the boundary, they corresponding to the states, like qubits, that's a linear theory. You can take the superposition of two states. So you can take linear sum. So we have the projective theory in the bulk and the linear theory on the boundary. And in general, we have this functor, maps such surface to transformations. And we have a bunch of relations for those braided charged strings. First of all the braids, they satisfy the random mass moves. That means they are really pictures in the three-dimensional space, but we are looking at the 2D projections. And then the charge can move freely under the strings. And since in the bulk is defined projectively, so you can ignore the scalars in front. So the charge can move freely. And those relations has topological meanings, and they are also well defined not only for qubits, but also QDs. But actually, the last two, the two blue relations are very interesting. They are only true for qubits, not QDs, and they are not from topological isotopy. And these two relations somehow tell us the difference between qubits and QDs. And I try to pursue that kind of phenomenon for a while, and here are the two examples. Whether the qubits has something different with QDs. And here, okay, they have some difference. And what's the significance of the two relations? Like the first blue relation, if you look at the crossing carefully, one is a positive braid, one is a negative braid. So in that sense, we can change the braids from positive one to negative one by adding a pair of charge. And since the charge can move freely, so we consider that as lower complexity. And this is very important because if we do not have this relation, then in the computation, we need to compute the value of some links. And usually it's very hard to compute that. But with those relations, we can get rid of the complicated theory of knot theory. Essentially, they become unknowns after this relation. And then it becomes pretty computable. And on the boundary, we have linear relations. As we mentioned, we have this resolution of identity. And for the braid, we have another linear relation. And we call those relations the boundary relations. And for the gradient operator, it tells neutrality. Now we rewrite that not using this the orange cut. Instead, we write this through strings in a cylinder in our terminology, and we use the holes to indicate the shape of the surface. So between two holes, the diagram is essentially living in a cylinder. And then we have the following relation. We can remove a hole. We write in this diagram the through string, two and three strings, as a linear sum of two terms, the same as the gradient operator. And from that, we can derive another relation that also change the shape of the surface. We call the string genus relation. So that means if we have a hole in the surface and the hole is surrounded by a closed string, then we can remove both up to scalar. And first, we found this relation from a purely mathematical point of view, and it has some significant consequence. But we are not sure whether this is useful in quantum information. But eventually, we found this relation is actually very useful in quantum information. So I use this relation to design quantum error correcting codes on quantized graphs. And this is a crucial relation. But in this talk, I will not talk about detail of that. I will talk about a different perspective of this string genus relation. It's the only bulk relation that's changing the shape of surface. We'll explain what's the meaning of that. So why we are interested in those bulk relations, namely the relations without linear sum, and in particular this string genus relation in quantum information. Okay, it's about the complexity, and somehow we study the complexity in a pictorial way. In quantum theory in general, we are very interested in the complexity, whether something can be computed in polynomial time or exponential time. So polynomial time usually means efficient. And we want to show the quantum advantage to somehow give algorithms that can solve problems in polynomial time by quantum computer, but not classically. So we want to understand the difference. Now from this pictorial point of view, somehow we can describe the boundary between polynomial and exponential in the following way. Say if we want to compute the measurement of circuits, or in general, the value of the tensor network or partition function of some models. We need to compute a closed diagram and evaluate that closed diagram using certain relations. And if we use the usual qubit basis and represent everything as matrices, then we need to compute that using exponential time. And the idea of tensor network is you can have additional diagrammatic relations, and then you can reduce the tensor network in a more combinatorial way, and that may give you a polynomial algorithm. So those bulk relations without linear sum is somehow a combinatorial relation, and the cost is usually polynomial. And the boundary relation gives you a linear sum, and the cost is exponential. For example, if we have a surface with genus n, so we have n holes. Now using the neutrality relation, we can remove a hole by write the diagram as a sum of 2. Now after removing n holes, we will have 2 to the n terms. And that's already exponential cost. So how to save the cost? We have to use the string genus relation to remove the genus, because that doesn't go grow exponentially. It's a bulk relation. And all known bulk relations that can change the shape of surface reduced to the string genus relation. And that's why we found it's so important. So somehow it's the only relation that tell you all those bulk relations changing the surface. And in particular, if we look at the tensor network generated by the poly XYZ, the Hartman gate, S gate, and the identity tensor, the tensor network is called the Clifford gate, and the corresponding circuit is called Clifford circuit. And it's well known that such circuit can be simulated by classical computing in polynomial time. This is the thesis of Gaussman in 1995. And in general, for tensor network case, the algorithm is known as the ZX calculus. So we refer to the paper of Bob and Dukan. And what we can show in joint work with Xungao, Jaffe, Yunxiang Ren, and Shengtao Wang is using the bulk relation in the QAnon language above, we can efficiently simulate a Clifford tensor network. And the reason is the following. All those bulk relations actually implies all the tensor network relations in ZX calculus. And once again, I want to emphasize that all the relations that change the shape of tensor network, namely change the shape of genus, the surface in QAnon language, all of them comes from the string genus relation. And the rest part are essentially topological isotopic. The string genus relation is pretty powerful in that sense. Well, those Clifford gates are very important, and actually they are fault tolerant in topological quantum computation in Kitaev's Tori code. Well, unfortunately, the Clifford gates are not universal for quantum computation as we mentioned. They can be simulated classically, so they do not show the quantum advantage. Well, if we have the Clifford gate and another phase gate, then they are universal. So then the question is, okay, in the QR language, whether we can also understand the phase gate in a pictorial way and study additional features, and then combine the two together. One side we have Clifford, the other side we have phase gate. Once we combine them together, we get everything. And the answer is yes, the phase gate also has very beautiful pictorial meanings. The original motivation is given by this Euler formula. Any one qubit gate, SU2 matrix, can be represented by the product of 3 phase gates in X and Z basis. So we can take this rotation in Z basis, and then in X basis, then in Z basis, ZXZ. So that can represent any SU2. Well, if we change the order of X and Z, we get another relation. So this gives you two different representations of a unitary SU2. Well, in the QAnon language, each gate is given by 4 strings. And the poly Z gate only use 2 of them. We will have a parameter on the crossing, the theta 1, on the first 2. And for poly X, it's used the second and third. So essentially, to represent a single qubit gate, we only need 3 strings. And then the above equation tell you the following equation on the first 3 strings. The last one is free. And more important stuff is, if we just check this relation on the first 3 strings, not check the action on the qubits, just check this diagrammatic relation in the CAR algebra with 3 generators, it also holds. So this Euler formula actually comes from this Yang-Baxter equation in the CAR algebra. Now here the phase can be written as a linear sum of 2 projections on 0 and 1. So for the phase gate, now we have a very good pictorial meaning, a pictorial relation. That's the Yang-Baxter equation. And I think we all like this kind of equation. We know its power. Now let's see what can we do using this Yang-Baxter equation in quantum information. The following observation comes from Xungao. It's very important for me to understand this stuff. So first, he observed that there is another state called W state in quantum information. It's 1, 0, 0 plus 0, 1, 0, and plus 0, 0, 1. And for a long time, we thought there's no way to represent W state by good pictures in the QAnon language. But Xungao tells us, okay, there is a good one. So what's that? It comes from this star triangle equation. In general, if you look at the tensor on the right, this is notation in tensor network. We use the 6th string. So the trivalent vertex is the identity tensor 0, 0, 0 plus 1, 1, 1. And the red bullet is this phase gate e to the IC tax. Now this tensor represents a 3 tensor. And if we take the angle theta to be pi over 3 for all the 3 bullets, then the state is a W state. And the star triangle relation tells us for this tensor network, this triangle, we can reduce that to this trivalent vertex on the left, but the phase will be changed. So the 6 bullets may have different phase in general. Well, what happened in the QAnon language? If you see a phase in the tensor network, and then in the QAnon language, the phase corresponding to a hole in the surface, because each line is a cylinder, and the line go around the phase means you have a cylinder go around the hole. So if you look at the picture at the bottom, the triangle corresponding to this picture with a hole, and the picture on the left side, the star corresponding to a picture without a hole. Why this relation holds? If we look at this in the QAnon language, we can see the details. What happened for this star triangle relation? It's the following. In the first step, we use the Yang-Baxter equation for those black lines. And then we apply the string genus relation in the middle. And then we go from the first picture to the last picture. And this is exactly the star triangle relation. So there are 2 significant parts in this relation. First, we can reproduce the star triangle relation using the more fundamental Yang-Baxter equation. And secondly, once again, the relation that we can change the shape of the tensor network or the shape of the surface is the string genus relation. Now, in general, if you look at a planar graph, the tensor network, planar tensor network, and all the edges are labeled by the red bullets, this phase gate. And then using the same argument, in the QAnon language, we will have a diagram without holes because all the holes are removed by the string genus relation. And then those diagrams becomes a 4-valent graph. You can think about that as a 2D projection of a link. And it has parameters at the crossings. And moreover, for those crossings, we have the following relations. The last one is the Yang-Baxter equation. And also, when we rotate the crossing, it's again a crossing, but the parameter has been changed from theta to theta hat. And when we cap the crossing, we get a vertical string up to a scalar. And when we combine two crossings, we add up the phase. And all those relations together, we call it the Young-Baxter relation. It can be considered as a generalization of the random mass move 1, 2, 3 for a braid. But for the random mass move 2, the multiplication of two crossings is not the identity. It's another crossing. And it has the parameters. And then in my thesis, we already know any closed diagram can be evaluated using the Young-Baxter relation in polynomial time O to the n cube. So in this way, we know those tensor network can be evaluated in polynomial time. And this algorithm was also well known as, well, not this algorithm, but the result was also well known using the FKT algorithm. Namely, you can evaluate such tensor network using Pfaffins of certain matrices. But here we give a different way to prove this result. And the advantage of this algorithm is the following. Those relations are local relations. So you can combine those relations together with the genus we mentioned above. Since in quantum information, we also need to study the relation with such like phase parameters and the relation with the genus. So this algorithm is very useful in that sense. We can combine both. So in total, we have 3 categories of relations. First, for the braided charged strings. And second class, we have the surface with genus. And the third class, we have the parameterized crossings. Well, if we combine the first 2, we know it's Clifford, and it can be simulated classically. If we combine the first and third, it's the match gate. It can also be simulated classically. And if we combine all 3, then it's universal, we get everything. And we believe it cannot be simulated classically. So actually, the first 2 families, Clifford and Matchgate, are so far the known 2 big families of tensor networks that can be simulated classically. Now, whether we can find something new beyond the 2 known families. So we want a class of tensor networks, including the parameters and the genus. Now here is an example. Well, the picture may look very complicated, but the key point is, okay, this is actually a square lattice, and the blue part corresponds to the hole. And between each 2 holes, nearby holes, there are 4 through strings. So this picture actually corresponds to a tensor network on a square lattice. And the crossings, the red crossing has parameters, and the black crossings are braids. And you see in this picture, there are 12 holes in the middle. They are surrounded by strings, so you can remove them by string-genus relation. But there are 4 holes at the corner. You cannot remove that. And actually, if you look at the two of them, they are surrounded by a string. So each essential genus, or each pair of essential genus, is surrounded by a string. And as we mentioned, the only relation that we can remove the genus without using the boundary relation is exactly the string genus relation. So in this picture, there's no way to remove the genus using bulk relation. So that somehow tells you this graph essentially has genus and parameters. It goes beyond the Clifford gates and the match gates. Well, for this family, actually, we can also compute this tensor network, the value, in polynomial time. So this is the local part. You can write this as a local piece of a big square lattice. So how do we do that? We cannot use the bulk relation directly, but instead, we can use this neutrality relation to remove a hole as a linear sum of 2 terms. And we do this at 1 time. So now we have 2 diagrams. And then the magic is the following. Once you remove 1 hole, then you can always find another hole surrounded by a closed string, because originally the closed string go around 2 genus. Now you remove the 1. So you can remove the other using the string genus relation. This is kind of a chain reaction. Once you remove a single hole, then all the holes will be removed by the string genus relation. And this gives you a polynomial algorithm. And more precisely, this model can be considered as an Ising model for interacting fermions. And its partition function can be computed as a sum of two partition functions of free Fermis. So if we want, we can actually study further properties. But so far, we studied this by considering it as a large family of tensor networks beyond Clifford and match-gates, and it can still be simulated classically. So what we mentioned is how we understand different concepts in a pictorial way, and then we use somehow virtual concepts like the string-genus relation. It has no direct meaning in quantum information, but eventually those virtual concepts are very useful to design like communication protocols, quantum error correcting codes, or the same-level tensor networks and some exactly solvable models. This is kind of the usage of the square root of -1 at the beginning. It has a mathematical meaning, but later we realize the importance of that in physics. And using those pictorial notations, we can also understand other concepts, and that's the work in progress, a quantum circuit compiler to simplifying circuits. And here in particular, since we're looking at those diagrams, we may have a global simplification of the circuits, not just local manipulations. And also we may have polynomial algorithms or other combinatorial problems, and maybe graphical problems. And we may even get real quantum algorithms, since if we can show the diagram essentially cannot be reduced in polynomial time, then maybe it's really, if we can do this if we can compute it as a composition of unitary gates, namely we can compute that by a quantum circuit, then maybe we can find a new quantum algorithm. And maybe not only one, but a family of quantum algorithms in that way. Somehow we want to understand the boundary between classical and quantum in this sense. And also we can get exactly solvable models, and we are looking for a physics interpretation of those meanings. And those, those are the work related to quantum information. And what gets more interesting is this string-genus relation also has an important role in statistical physics. And I found that recently, and it's actually last week when I prepared for this talk, and also want me to present something really new. Now we get to the really new parts. So first, I will again talk about the Z mod 2 case, and that corresponds to Ising model. And we look at the classical notation. We have a square lattice on the left. And at each vertex, this 4-valent vertex, we have a spin up, spin down. And at each edge, we have a red bullet. It's the phase gate, e to the s theta x. And that represents the interaction of the spins. And then the value of this tensor network, if you want, you can take periodic boundary condition. The value of this tensor network is the partition function of the Ising model. But first, we can look at this tensor network in the QAnon language. Let's see what happened. So in the QAnon language, that means we need to replace each thick string by 4 parallel strings in a cylinder. And the red bullet is a crossing with parameters. And to do it in this way, each face in the square lattice becomes a hole in the surface in the QAnon language. And as we imagined for the match gate case, those holes can be removed by the string-genus relation, because when we represent this red bullet in the tensor network, the first string and the last string are free. They are the purple string in the picture. And once you combine them around the hole, you get a closed string. And then apply the string-genus relation, you can remove all the holes. And then we get a picture, a planar picture without holes. And the value of this planar picture is the partition function of the Ising model. And this was actually studied by Wong Jones in the framework of planar algebras already. He knows the partition function can be done in this way, can be computed in this way. And in particular, the Kramer-Warner duality can be understood by switching the shading. So here in the planar picture on the right, the shaded part corresponding to the value of spins, you can have spin up, spin down. And if you switch the shading, you go from the lattice to the dual lattice, and you also get the partition function on the dual lattice, but the parameter will be changed. It moves from low temperature to high temperature, and the critical temperature is given by the fixed point of this Kramer-Wading duality. And in planar algebra, that means you locally look at the parameter at the crossing. You take a 90-degree rotation, that's the Fourier transform. And the critical temperature is obtained at the fixed point of the Fourier transform. So the QAnon language gave us a bridge that can translate in a very natural way from tensor network to the spin model. Well, in planar algebra, actually, I'm puzzled for a long time. How do we understand the spin in the shaded region? The spin is not defined in planar algebra. It's defined in some general framework called graph planar algebra. But the computation there is usually exponential. It's like we use the usual basis 0 and 1 to compute tensor network. So it's very inefficient to compute, but it can be defined mathematically. And then I want to know whether we can use something like the string genus to compute such things in a more efficient way. And how do we understand the spins pictorially? So that's another concept I want to understand in pictorial way for a long time. And until last week, I get it. And I call it a topological spin. So in the shaded region, instead of putting the abstract notion, this spin J, we put the string genus, the genus with double string, and with the label. And this label is the vector, the qubit basis 0 or 1 to indicate spin 0 and 1. And in general, this is just a picture. It's actually a pretty good picture. And then the first result is the partition function of Ising model with spins, with fixed choice of spins, is given by this picture with the string genus in the middle. It's exactly the value of this picture. It's similar to the original one without genus, but now we can talk about the partition function with spins. So in particular, using this notation, we can discuss the phase transition. We can discuss the boundary condition, different boundary conditions, and the value at different spins. And also we can discuss the correlation function for two spins and the exponential or polynomial decay. And many concepts in statistical physics can be formalized after introducing these topological spins. And in particular, since we know we have the string genus relation, that means after we add the string and the genus, if we take all possible spins, then we have a genus surrounded by two strings, and we can remove that without changing the partition function. That means we can embed the planar graph without without genus into a surface graph with genus, but without changing the value of the partition function. So this gives the embedding map. It's actually a functor from the genus zero theory we call planar algebras to the higher genus theory we call surface algebra, and that preserves the partition function. And the important part is, from the physics point of view, if we know the partition function, somehow we know everything else. And this is true. Once we know this map preserves partition function, it preserves all the categorical properties. So this is a functor of the corresponding categories. And indeed, this function captures a very remarkable result in subvector theory. It's called the embedding theory. Namely, every planar algebra can be embedded into a graph planar algebra. And in this approach, the planar algebra lives in the theory without genus, and the graph planar algebra lives in the theory with genus, and it's actually a sub-theory of this more general one. And this actually will give a one-line proof of that very important result. So in their original work, they need to verify certain algebraic condition locally, showing this is a functor, this is well defined. And here we only need to show one thing, that this map preserves the partition function, and everything else are just consequence. And this is true because this embedding map is just adding the string genus relation in the shaded region, namely we take all possible value of spins. Okay, well, that's for the Z-mod 2 case, the Ising model. What makes it even more interesting is we can look at other models, like from conformal field theory. we know given 1 + 1 conformal field theory, its representation category is a unitary modular tensor category, also equivalently captured by a 2 + 1 topological quantum field theory. And most people believe that there is a duality between the two. From CFT, you can get TKFT, and also the other way. But however, the inverse is highly non-trivial. Since TKFT somehow is combinatorial, the data is discrete. And then you need to define a reasonable continuum limit of some reasonable lattice model to get a quantum field theory, and then a conformal field theory at critical temperature. And in particular, this modular tensor category has very abstract data defined by certain axioms. So it's not apparent how to study them on a reasonable lattice model. Now, using the previous approach, we have a very natural generalization of the Ising model, but for quantum symmetries. And the spins are given by the simple objects. The interactions are given by morphisms. And this is pretty conceptual. And in particular, we can get this lattice model for quantum spins. We call quantum spin lattice model. And we can study those concepts in statistical physics, like spins, interactions, partition function, correlation function, and in general, endpoint function, and also the limits in large scale or continuum limits, and maybe also the renormalization in the future. And another crucial point is, in this pictorial approach, we can see the crime-module duality is encoded inside the picture. So there is a hope to find the critical temperature given by the fixed point of the Fourier transform. So maybe it could be very hard to prove that, but at least finding the value may be possible, so numerically. So, and this program is studied in various topics. In subject theory, we call it the Reconstruction program. We want to construct a quantum field theory or conformal field theory from a subfactor like the H-group subfactor. And now at least we get a reasonable model. And a very good sign is we mentioned at the very beginning, we can prove reflection positivity. And this is crucial to get quantum field theory and also to prove like exponential decay of correlation functions. And in the work with Arthur, our proof of reflection positivity in this pictorial framework is really robust. It just works in a very, very general situation. So don't worry about this condition. We can prove that. And we already know in statistical physics, this reflection positivity has a lot of consequences. So maybe we can try that first. We can prove those results for more general models coming from those quantum spin chains. And if we are lucky, maybe we had a chance to see the conformal field theory eventually, maybe 20 or 30 years later. Thank you. And happy birthday, Arthur.
Thank you very much, Zhengwei, for a very interesting talk. I'm sure there are many questions. I have many questions because I'm certainly no expert in this area. Maybe I could just start off with since many of us know something about reflection positivity. So, for example, is it easy for you to recover the results of Dyson, Lieb, and Simon for the antiferromagnetic Heisenberg model?
Antiferromagnetic, I'm not sure.
Yes, yes. Of course, the ferromagnetic is presumably not true, but the antiferromagnetic one is the one they proved a phase transition for by establishing a version of reflection positivity. I just wanted to know whether that fit in very easily into your picture.
I cannot give an answer now, but maybe we shall try that.
Yeah. So there may be a way of doing that with the picture language program, which is very natural. So that was really my question. I know that Daniel Ulci had some way of doing it using his pictures with these how would I call it, cycles representation, the permutations representations of some of these models. Anyway, yeah, so maybe I should begin with seeing what I'm sure there are many questions the audience has, so please jump in and ask.
I cannot see the question.
No, I'm not. I can continue with questions. I have no shortage of questions, but I'm sure other people who are much more knowledgeable can make very useful comments.
You can just press the space bar to unmute yourself temporarily.
Well, let me continue for a minute so other people maybe can collect their thoughts. So you have this at the very end. You have this relation between topological quantum field theory and in 3 dimensions and 1 + 1. So what is the status of that? I mean, is this supposed to be a 1-to-1 map, or is it? I don't know so much about this connection.
From rational CFT to TQFT, this direction is more or less clear.
Okay. Yeah.
The other side is very hard.
I see. I see. So you don't know that it's onto, in other words, right? You don't know that you may have topological field theories for which you have no corresponding conformal field theory.
It's not clear, and there is they call the golden line. They can do something for the Ising case. That's why I mentioned Ising case.
Yes.
And then here the point is whether we can somehow formalize all the concepts appeared in Ising model, but for those quantum spin chains or quantum spin lattice. And the first step I'm trying to understand is exactly the spins. And I talked with Arthur at the very beginning, I think even in 2015 when we met first. And I know, okay, if we want to construct some reasonable field theory, we need to understand the boundary condition, the correlation function, and things like that. But all those things are defined based on the spins. It's not just a single partition function. It has additional data. And then I have the difficulty to understand the spins. I try to use the graph plane algebra to do that, but it's very hard to compute something on graph plane algebra because all the computation goes exponentially. It's very hard to handle. But now this topological notion gave us a very good way to prove something. So it becomes reasonable now to prove, like, for example, if we want to prove the correlation function has exponential decay when the temperature is low, I think that's possible.
Yes. And so you mentioned Ising, but how about Potts? I mean, Ising is well known to be, basically free fermions or a quadratic. You can express it in terms of Pfaffians, at least if you don't have a magnetic field. But what about, and you said, well, then you can compute the Ising model or some additional variants of it. What about Q-state Potts model, for example, for Q equals, I guess Q equals 3 is quite interesting. What can you say about that case?
So far, I cannot say anything about any general case. I can only say, okay, here I feel it's the right definition, and I can write down statements. But
yes.
The proof is not clear.
But does your algorithm where you can compute complexity somehow tell you that you, or suggest that you can compute it, the partition function for 3-state Potts somehow polynomially fast or something like that?
The idea is in this approach, we may not need to compute the partition function numerically because the partition function has a diagrammatic representation. So we can study the property of the partition function using the diagrams directly.
Yes, but then what will that tell you about the system if you can't make some kind of calculation?
Like for example, if we want to look at the Kramer-Wallner duality of the partition function, we do not need any computation. We only need identification of this partition function on the lattice and dualities.
Yeah. Well, I guess we know the Kramer-Wallner duality for 3-state Potts, right? That we know quite well.
Yeah, and for example, For the general case, not for Ising case, I can tell. It has a Cremorne divided as well. That's something I can tell now.
So Zhengwei, you talked about planar algebras and surface algebras. Have you thought at all about the higher dimensional case?
No, it's really two-dimensional case, and more or less related to the last question I mentioned. It's 1 + 1 CFT and 2 + 1 TCFT. It has a very special dimension. And I'm not familiar with the higher dimensional case beyond that.
Yeah, so
Mhm.
I have just a very general question, since I really not very knowledgeable about this area, even though I've heard you talk about it and Arthur talk about it. My question is, there are many sort of I guess graphical or pictorial representations of partition functions and other things for quantum and for classical systems. So in what makes what you're doing so different from the or useful from the other pictorial representations?
Sorry, I didn't catch your question.
Yeah. So there are many. You can write Ising model down in terms of pictures also, and various there are various loop representations for all kinds of models in statistical mechanics. Now, and those are pictorial representations of spin systems using quantum spin systems. So your pictorial representation must be somehow a little bit different from those, and I wanted to know what the advantages were in yours over the others. Does that my question clear now?
Yes. I can explain this using one example. Like in the Levin-Wien model, they call that the string net condensation. And in their approach, somehow the pictures look pretty similar. And that's the part that may be confusing, since we are using pretty similar, but the point is that the interpretation is quite different. So finally, we end up with different statements. And in the Levin-Wien model, when they consider the string net condensation, they use the morphisms in the tensor category to generalize the spins. And for a long time, I don't know whether that's the natural generalization, since somehow I feel the object should correspond to the spin, and the morphism should correspond to the interaction. And why they use morphisms to represent spins? So I'm puzzled for a while. And so here I can study their model, but I interpret the object as spins and the morphism as interactions. So they can look at the same model but with a different physics interpretation.
And what advantage does that give you thinking of the spins as morphisms?
One advantage is then we can talk about like correlation function. Like we can put two spins in the lattice, and actually in the two different faces of the lattice, and then we can move the strings far away, and then we can count the correlation function and say whether it has exponential decay or not. We can look at those properties. And
so in other picture or graphical representations of system mechanics, for example, in percolation or also in various quantum Heisenberg models, you can see you can tell whether you're at criticality by looking at the well, for example, if you have macroscopic loops in your system, and so that's a very pictorial way of understanding whether you have short loops and you're at the high temperature phase, you have very long loops and you're at the low temperature phase. And I'm just wondering, is there something analogous to that in your picture?
Yes.
So you can see a phase transition by looking at the geometric structure of the loop.
No, it's much harder since the loops are replaced by a closed diagram.
Okay.
So for the Z mod D case, for abelian, the story is pretty similar.
Okay.
But still, the counting problem is also harder than the Ising case and Z2 case. And for the non-abelian case, it's much more complicated. The loop is replaced by a closed diagram. It's no longer a real loop. It's just a closed graph. But still, we can count something like that. And I'm not sure, but that's somehow my hope, why I expect this. I mean, we can prove something about the correlation function using this pictorial notation.
Mhm.
And actually, I was also thinking about the renormalization. Maybe there's a way to show the renormalization group is well defined in some sense, but I didn't get it.
To make that a bit more quantitative, in the Clifford case, you had polynomial calculation in n cube. In the other case, what would be do you know the power of n you need for your more general diagrams?
So, sorry, I didn't catch.
For the Clifford case,
Yes.
Yeah. Polynomial computability in n cube, the third power. Sorry.
Your microphone is not working.
Sorry. Yeah, well, I'll try to change. Yep. Yeah.
Do you understand me now?
Yes.
And I have here. Yeah.
Okay, fine. So in the Clifford case, you had possibility with n cube. So third power of the input.
Yes.
In your more general case, do you know the power of n?
More general case is also n cube.
Oh, I see. Because for the Potts model or so, one probably would conjecture that the difficulty of the computation might be larger for, let's say, for the three-state Potts model.
Oh, so for the general case, this case may not contain the Potts model. When I say general case, it's still for Z mod 2. But
Yeah.
just the interaction becomes different.
Yeah, okay, thank you.
Hi, Zhengwei. This is Sean. I have a question. So you said somewhere that the QAnon language realizes the Ising TQFT. I just wonder how you can see this point. For example, can you like in your formalism, can you compute the partition function of three manifolds? Yeah.
Yes. Yes. The partition function of three manifolds corresponding to the value of some graphs, depending on the triangulation. And
yeah, but like is this also explicit in the QAnon language? Okay, and this recovers the Ising TQFT. You said.
yes, like actually, the surface algebra is pretty close to the 12-year TQFT. We have some additional data. If you forget the braid, then if you only remember the string, the surface, even without charge, then you can actually remember the 12-year TQFT.
Sorry, you mean trivisual TQFT from Ising or the the Rashidin tribe TQFT?
No, 12-year, not Rashidin 12.
The trivisual is you realize the double is a double theory. Like you. Oh, okay.
So only when we talk about the spread, we use the somehow the well, it's kind of we use the pictorial properties in both TQFT, but in different way. and this is neither 12-0 or reciprocating 12. If you forget the braid and forget the charge, and then this reduces to the 12-0. But it's a little bit more than that, but it's not the reciprocating 12.
But what is it? Is it a TQFT in the full case, in the full generality?
Well, you see, this is not the TQFT in the usual sense. For example, like you have those additional data on the surface, and the data have this braid. Well, let me see how to explain this.
Well, I mean, you can use the notion of extended TQFT if that's
well, even extended TQFT is essentially a planar algebra. It has no braid. Say if you have this surface, and you only have 9 intersecting strings in the surface, and for the face you have colors. That's for the fusion category of the extended TQFT, and the string corresponding to the bimodules, the simple objects. And then what we can put as inputs and outputs will be the morphisms. And the string connecting two boundary points just means you glue the boundary of the n-gang in the TQFT. Well, usually we have the triangulation of TQFT. That means the disk in the surface will have 3 boundary points. If you only look at triangulation, but here you may have n-gangs in general, and that is a one-to-one correspondence between those surface algebras and the 12-0 TQFT. But in addition to that, here we can have additional labels given by the braid and charge. And even though we see the braid, but this is not really the reciprocating 12, so this may look confusing. That's the way we use it.
Okay, I see. Can you construct like other TQFTs? I mean, like TQFTs based on other modular categories?
Yeah, we can get the 12-0.
Like all of trivisual?
Not 12-0.
Sorry, you mean like a trivisual based on any spherical fusion category?
Yeah, any spherical fusion category. Yes.
Okay, that's good to know. But you didn't talk about this in the talk, right? I mean,
no,
like,
this is what I call surface algebra. That theory is more or less parallel to the theory of 12-0 TQFT. On one side, we use triangulation of the 3 manifolds. The other side, we use surface. But we can have a piecewise translation. Actually, the string genus relation has a special meaning in 12-0 TQFT. Namely, in the triangulation, you have a line in the middle of your manifold. And you can remove that line if the line has all possible labels. And you can translate that condition in this framework that becomes the string genus relation. But there is a tiny difference. It's the single string genus relation, and that corresponds to another kind of line. It's the AB bimodule, not A bimodule in the 12-0 TQFT. Okay. There is a one-to-one correspondence between the mathematical structure if you ignore the braid and charge.
Okay, got it. Thank you.
Yeah, this is Rad. Is there a way to make connections between these non-commutative algebras and non-commutative geometry that Alan Kearns was talking about?
I don't know.
Okay.
We haven't thought about that.
Okay.
But there's another conceptual motivation for me to study those tensor networks. Since somehow I feel that subfactor theory tell us the local properties, like the symmetry of a spin and local interactions. But we do not discuss in subfactor theory is the shape of the lattice. Yeah. And that's what I learned from quantum information. We are very interested in that. So somehow we can think about local data is given by a subfactor in general, and the shape of the network is a different stuff that we miss when I work on subfactors here. I never thought about that. And then I say, okay, maybe we shall combine the two together. And I would think about that as a kind of discrete, like non-commutative geometry. Subfactor give you the discrete, somehow non-commutative symmetry, and the lattice give you the additional geometric structure.
I'm looking at it this way. To understand non-commutative geometry, these might be a good models to look at them. So, but again.
And actually, Occhiani has a very beautiful result. Say if we run the embedding theorem, if you take a planar algebra that embedded in a so-called graph planar algebra, it has a loop model called graph planar algebra. And then what's the image of this embedding map? The image is the flat part in the graph planar algebra with respect to a connection. That indeed has a very beautiful geometric structure. It's corresponding to the flat connection for conformal blocks.
Do you have a reference for the paper?
The result is in the work of Yasu Kawaigashi, very beautiful paper, very long paper, so around 2000. Yasu is very generous to give Adrian a lot of credits on that work. And I don't remember the title, but the keywords are something like parallel groups, connection, parallel groups. This organic
connection. Okay, I got it. I'll check that. Yeah, thank you.
Are there some other questions or comments?
Also, I cannot hear. You mute.
Yeah. Oh, sorry.
I said there are all these other experts here. Roberto, do you have some comment?
No comment. Only comment is happy birthday.
All right. Well, if there are no further questions, and comments, let's.
Well, I would like to thank
please.
Zhengwei, because I can't think of a nicer birthday present than this talk. It's absolutely wonderful. Thank you very much, Zhengwei.
Thank you, Zhengwei. It was very, very interesting, and many things I need to talk to you and Arthur more about. But yeah, it gives me an opportunity to formulate even more questions. So it's wonderful. Okay, Zhengwei, thanks very much, and happy birthday, Arthur.
Thank you. Happy birthday, Arthur.
In January.
Yep, see you then. Look forward to it.
Happy birthday, Dad.
Margaret.